morning or afternoon or evening, everybody. The next lesson in this grade 11 university class video series, nuclear fusion. The last lesson was on fission, which I think is less known about. People are often surprised, I think, that nuclear power is not nuclear fusion, it's nuclear fission, breaking apart materials. But we'll see here that nuclear fusion is when you combine two light elements, and in order to combine them, you have to really force them together with a lot of energy, right? So in order for nuclear fusion to happen, you have to like push them together hard enough to overcome that repulsion force that exists between all atoms, and it's really not easy to do that. It takes a ton of energy. So the heavy elements like uranium, plutonium, things like that we have on Earth, they were made through nuclear fusion somewhere other than here on Earth. We then just have them and are able to split them apart. We figured out how to split them apart and release that energy that was used to put them together. And so that energy to put them together happened in things like stars and supernova and things like that. Take an astronomy course to learn more about all that stuff, right? But basically, it's pretty simple. The idea that there's in a star, there's a ton of gravity, a ton of energy crushing protons and neutrons together, so crushing hydrogen atoms together and causing them to fuse together and become helium, roughly speaking. And when that happens, it releases a ton of energy. And so stars and supernovas and whatever other astronomy or astronomical processes for fusion is definitely one thing to know about. Um, particle accelerators here on Earth can actually cause nuclear fusion to happen very small amounts and very briefly. But you collide particles such as a proton or whatever you're accelerating around this loop here, right? So you have a proton maybe that accelerates around and comes here, and one that goes around and comes here, and then they are directed to smash together with a huge amount of energy, enough to make them actually fuse together, and that energy that goes into the reaction actually causes new particles to be created out of the energy. Obviously, E equals mc squared coming into play there. So you have your hydrogens fusing together to make heliums, and it's a process. It's a proton-proton chain reaction. It's not quite as simple as just take a hydrogen and smack them together. You get helium, but yeah, it's going to involve a lot of those reactions we talked about recently. Notice how there's a neutron there, right? So obviously there was a reaction. This might be an electron or neutrino given off, so that could have been one of your beta negative decays or beta positive decays or something, right? That we know about. And then there's a gamma ray going off, right? So we have this high energy product, and it releases a gamma ray, and so on, right? So this is just energy given off, and that's what's happening. Nuclear fusion, right? So not all nuclei, not all atoms can release energy when they're fused together. Not all can release energy when they're split apart either, right? So this graph below is your classic binding energy versus mass number graph, and it is critical to understanding how energy is released or absorbed when nuclear reactions happen. So usually we think of it as releasing energy, of course, right? Because that's what we use nuclear. That's the whole point of nuclear knowledge is about ways, sources of energy, releasing energy, either to create electricity or to blow stuff up, right? So to understand this, we need to understand how changes in the binding energy. Remember, the binding energy is the energy that's holding the nucleus together. So how changing the binding energy is related to releasing or absorbing energy. Because textbooks always just say, oh, okay, so we went to a higher binding energy. Oh, so that means we've released energy. But I always was wondering like why that was, and I never got a good explanation, and I finally managed to sort of make sense of it. So I'm going to share that with you, all right? And so binding energy and what it has to do with releasing energy, okay? So if we change binding energy, we're either releasing energy or absorbing energy. So if you think about masses, it's pretty easy to visualize the moon and the Earth, right? There's lots of gravitational potential energy stored in this situation, right? The moon could collapse, accelerate towards the Earth if it wasn't orbiting, and it would smash into the Earth. It would release a ton of energy. So if the moon wasn't orbiting, that's what would happen, right? I have a little animation here of the moon crashing into Earth if you want to see it. Just try to grab it quick enough here. just picture, the animation of what I'm describing, the moon accelerating towards the Earth and crashing into it. They should show it going faster and faster, but it's just an animation, right? So picture, the amount of energy that would be released if that were to happen. It isn't going to happen, and thank goodness, right? But yeah, there'd be a ton of energy released. Right? So I'm just trying to illustrate the idea. So as the masses are attracted toward each other, the stored energy is released and converted to kinetic energy and heat and so on. Eventually, that lump left over would cool down and that energy would radiate out, and that final state has a much higher binding energy. It's held together more tightly, of course, right? The moon is held together more tightly when it's a part of the Earth than when it's up orbiting the Earth. Right? It would be a lot less energy to get the moon way away from the Earth if it's in orbit than if it was like plastered in part of the Earth itself. Right? So that's this is a high binding energy state, right? And notice that, of course, going to a higher binding energy state, going this way, right, released energy. And that's the same idea with same idea with atoms. Okay, so if you're reversing that process, if we tried to go to a lower binding energy, it would take a bunch of energy. So it takes energy to move this way. Okay, so this is your binding energy per nucleon, and this is your masses. So we're going from an atomic mass of 1 or 0 being hydrogen all the way up to uraniums and plutoniums. And so iron is at the peak. Okay, so iron is the final one, where if you're combining these two to make a heavier element, then you're releasing energy all the way up to iron. And I'll show that a bit more. First, I'm going to illustrate one more way of doing this. So gravity is probably easy to visualize anyways, but it's fun to play with magnets. And so I have this video of the idea of the potential energy between these two magnets. So this is a super strong magnet, and then this is a whole bunch of tiny magnets, right? And so they're going to attract each other super strong. So if I type in one giant here, probably come up easy enough. One giant, probably looked like it was going to have it anyways. So this is a giant neodymium, or however you say it, magnet, and he's gonna show it crushing, yeah, there you go. Right, picture that energy is released there when they get stuck together. And in fact, if you had two big magnets, you'd have to be really careful not to get your fingers stuck between them, right? So the process right here, right there, yeah, right there, boom, right, all that energy got released, and then he shows it in slow motion, right? Kind of neat. So the idea is the same discussion. We've got, in this situation here, well, in the final situation, we end up with a lot more binding energy. They're clearly way more tightly bound. As separate pieces here, you can just grab this thing and walk away with it, no problem. Whereas in the video, you see him trying to pry these little magnetic balls off of this magnet. It's really, really hard to do. Right? Somewhere later on here, he's got, showed it. He was like trying to pry it apart. Yeah, there we go. This is the area where he's like working hard to like try and remove those magnets. So he's getting, he's fighting against that binding energy to release them and bringing them back to a lower binding energy state, right? Yeah, high binding energy was released, right? Moving towards a higher binding energy. So yeah, so that now we're just putting this in terms of atoms now, right? So when you fuse light elements together, right, you end up with heavier elements, and you end up with higher binding energy on this end of the curve. And so if you're moving to higher binding energy, you're releasing energy. Here we have heavy elements. Well, they can fizz, they can break apart to produce lighter elements, and each one having a higher binding energy. So energy is released, right? So fission and fusion reactions can be highly exothermic, give off a lot of energy, right? You just have to start with small atoms for fusion and large atoms for fission. So just to be clear here, atoms A and B fuse together to make atom C, resulting in more binding energy, releasing energy. Here we have atom D, a nice heavy one, fizzes apart to produce two lighter elements, each with a combined total binding energy that's higher. And so energy was released when that happens. So this is nuclear fusion to release energy. This is nuclear fission. So this is what the sun is doing. This is what nuclear reactors are doing, electrical generation stations and so on. Right? Right. Yeah. So when we talk about the magnets being apart, how there's a lot of, magnetic potential energy there, or, easier to say things like gravitational potential energy. These elements here, where's my note? This situation here, there's lots of nuclear potential energy, just like masses or magnets that are far apart. Okay. Yeah, so the higher the binding energy value, this is, I'll probably gloss through this a little bit. It goes back to the entropy concepts, right? But when you have a high binding energy, that's a more stable situation. And so the things tend towards that, if you will, right? And so you can think of this as they fuse together to release energy, or they this one, yeah, if you're split apart, you're getting a less stable form, right? And so it's absorbing energy. That's the idea of in terms of entropy. If you are increasing entropy, then you're releasing energy. Okay. I'll leave that to you. I don't want to dwell on the entropy concept. I don't want to confuse you if you've already understood it in terms of what I've said already in terms of binding energy. So let's not worry about that too much. This is just a review of what I've said. And then so the mass and energy equivalence, we've already seen this, right, where you can just multiply by 930 to get the number, right? And so basically they're showing here, if you have a fusion reaction where you have hydrogen and hydrogen fusing to make helium, this is what the sun's doing, right? Then we have a certain amount of mass before and afterwards, right? And so you can find how much mass is missing, or how much mass is, what the mass difference is, right? So how much more mass there was at the start versus the end. So the mass that's missing, of course, is the energy. So you take that change in mass. So this, like, it's surprisingly easy to do once you understand what it means, right? We're just finding out the difference in the masses and seeing like there's missing mass. And so of course that missing mass is energy. So you just literally multiply by 930. That's your C-squared number in terms of mega electron volts and atomic units, right? And you get your 17.6 mega electron volts. You have how much energy released when a deuterium atom fuses with a tritium atom. And again, that's a really small amount of energy, but the sun does this a mind-boggling number of times every second, right? There's just bazillions of hydrogen atoms fusing together to make helium and so on in the sun. Okay, so that energy, of course, that's released came from mass all the way along. There's just other examples of this that you can go through. Okay, so same idea over and over again. There's extra practice. Okay, so you might hear about nuclear fusion for electrical power generation, and believe me, we wish we could do this. If this becomes possible, you can just take like water and fuse it together and release energy. That'd be amazing, because we'd have a limitless supply of clean energy. But the problem is, of course, it takes a ton of energy to do that, and it's just super hard to do as a sustainable process. So they've managed to make fusion happen, but you use more energy in the process to make it happen than you manage to harvest. The energy you manage to harvest out of it. And by harvest, I mean actually manage to use the energy to do something. It's never been sustained. You can't do it yet, basically. So they're trying, but I mean it's basically widely thought that it's going to be very difficult to achieve. So there's different processes here. You can try to confine a plasma in an area with a magnetic field and so on. But yeah, long story short, don't fall for the silly videos that say there's a car that can run on water, and it's not possible at this point. But it probably never will be, but unfortunately, but people have said that in the past and wrong. So yeah. So that is your nuclear fusion questions. Obviously, all of those, but you need to be able to do them. You need to be able to do them. You just don't obviously have to do all of them. Does that make sense? Anyways, yeah. So like I've said recently here, like and subscribe and all that stuff to be able to help get these lessons out to more physics students around the physics community, world, whatever. And that'd be cool. All right. Thanks again. Talk